You can plan, but sometimes things don't go as planned. We were hoping that Director Kratsios would show you first image. This observatory is the greatest astronomical discovery machine ever built. And we finally started working with it. This is the first image that we are unveiling to the whole world today. Thank you for your reaction. But now that we looked at this image, I have to reveal a fun fact. This image actually shows only a small portion of one Rubin image, just about 2%. In other words, the entire Rubin image is 50 times larger than what we are seeing here on the screen. So you may wonder, why didn't we show the entire image? Let us see why. Rubin Observatory, including its Simoni survey telescope in the middle, LSST camera on the left, and an exquisite software framework, is designed to make huge images rapidly. These three components you can see on the screen and their technological breakthroughs is what makes Rubin and LSST possible. Let us first have a quick look at the super agile Simoni survey telescope in the middle. You will notice the color scheme is matching everywhere, and indeed, my official Rubin tie is modeled after the telescope. Here you can see Simoni survey telescope inside the observatory's dome. The point of this short video is to demonstrate the amazing ability and agility of this 300-ton telescope. No other large telescope in the world can move this fast. It moves around in seconds. Other large telescopes take minutes. Let us now look quickly at the LSST camera. This big, beautiful camera is already in the Guinness Book of Records as the largest astronomical camera ever made. It makes huge images. As we just heard, just one Rubin image covers sky area equal to 45 full moons with its 3,200 megapixels. But that many pixels makes it very hard to display such an image. This is more pixels than the human eyes, your eyes, my eyes, can see. And this is the main reason why we could not show you the entire image right away, but only this small image shown in the bottom right. You can see its relative size to the full field of view in this small rectangle at the bottom. As Director Kratsios pointed out, we would need 400 high-definition televisions to properly display just one Rubin image so that your eyes could capture all the detail. That means covering a basketball court with 400 TVs to display just one image so that your eyes can see all the detail. But instead of looking at 400 TV screens or walking around the basketball court, our team has developed a powerful web display tool that we can use to move around our giant images. We can zoom in and zoom out. We can explore and admire details of any object you choose to look at. Next, we will look at a region of sky about twice as large as one Rubin image. It is centered on the giant elliptical galaxy called Messier 49. This region that will explore in a second is about 100 times as large as the first image we saw today. The follow video is 1 minute long, and we will first enjoy it without any comments. Then we will replay it, and I will comment. Enjoy. We will look at it again. Before we start, I want to say that the entire Rubin team is so excited about this data. We have been talking about this data for over 2 decades. It's finally here. Let's look at it again. Please pause. You can see here a universe teeming with stars and galaxies. The seemingly empty black pockets of space between stars in the night sky, when you look at it with unaided eyes, are transformed here into these glittering tapestries. There is barely a pixel in this image that doesn't have some light coming out. And only Rubin can produce quickly such large images with this much color and richness. Please continue. Play. You can see spiral galaxies, elliptical galaxies, clusters of galaxies. Please pause here. This is an amazing region. We need to stop here. I love it. Do you love it? Okay. Everybody loves it. Here you can see a stunning variety of celestial objects, from bright stars in our galaxy, ranging in colors from blue to red, to these nearby blue spiral galaxies, to more distant elliptical galaxies that are yellow and red in color. You can see how vividly these colors are, and that's very important for science. Colors of galaxies are very important because using these colors, we estimate distances to these galaxies. You can also note in this image that galaxies are not randomly distributed in it, but they are clumped. They show clumping and statistical details of that clumping, and distances to these galaxies determined from LSST colors will enable very precise, unprecedentedly precise studies of the expansion history of the universe and studies of dark matter and dark energy. That's what we measure, where these galaxies are, how big they are, and what are their colors. And in few years, LSST will be producing unprecedented cosmological results. Let's continue. And now you can see the full extent of that image. It's about 2 LSST or Rubin fields of view. And this is how we scan the sky, 30 seconds per exposure. There were about 10 million galaxies, close to 10 million in that image. Thank you. This slide shows again the whole area that we just looked at the end of video, with the first image from today outlined in the top left corner, that small portion where your eyes could tell the detail. Known objects here are annotated with their names, and you may notice that most faint objects do not have their names shown, and that's because they have not been studied before. Most of these objects have never been seen by people before. As we already discussed it, in this projection, you simply cannot see all the details in this image because our human eyes and our screens are not good enough and large enough. There is so much more in this image that you can enjoy, that you could see in that 1-minute video. And you can actually do it yourself later at home using our tool that we developed for this purpose. All you need is internet, and at the end of the presentation, I'll give you a QR code with a link. And now I'm talking to our colleagues and friends on the internet watching us through YouTube. At the end of the presentation, you will get a link, and then you can spend the rest of your day enjoying these 10 million galaxies. We hope you enjoyed it, but there is more to show you today, much more. Imagine now an image like what we just looked at, but imagine it 1,000 times larger. That would be half of the sky, or the entire sky visible from Chile. That 1,000 times larger image than this giant image we just looked at, this is LSST, Rubin's main goal for the next 10 years. But LSST will be so much more than just an image, even though such great large image, it will be so much more than just an image. And that is because every object included in LSST, about 40 billion of them, for the first time more celestial objects than living people on Earth. Every object will be imaged about 800 times during these 10 years that it will take to deliver LSST. And that brings us to the greatest movie of all time, LSST. Because we will have 800 different observations, we can take these frames, we can put them in a movie, a digital color movie of the night sky. As I said, Rubin Observatory is the greatest astronomical discovery machine ever built. So let's see quickly what makes it so uniquely powerful. Most importantly, it can scan the sky super fast, about 10 to 100 times faster than any other large telescope. This is like comparing the speed of your car to the speed of an airplane. That's what we are doing. Instead of driving around from east to west coast for many days, we pop on a plane and we are there in 5 hours. That's what we are introducing here. It took us a few nights to collect data we are showcasing today. With existing facilities before Rubin, it would have taken at least a year and maybe more. And LSST would take 1,000 years, which is obviously impractical, not 10 years. This is why we had to build Rubin Observatory. And so let's talk now a little bit about movies. We have a couple of trailers to show you. So objects, we make movies of the night sky to see two things, objects that move and objects that change brightness. So objects that move come in two flavors. Stars in our galaxy move, and they move slow. We detect it, but it's slow. Much faster objects are asteroids, and they are in our solar system. And so we'll focus now on asteroids that we discovered in those few nights of data. So here nothing is moving yet. This is just to show you a tiny portion of that image that we will zoom in to discuss asteroids. Nothing is moving here either. What you can see is two spiral galaxies. What you cannot see is that these two beautiful galaxies were photobombed by asteroids. Let us see how. Here you can see asteroids as colored streaks They are not satellites. They are asteroids that move during exposure. And this color image is made by combining many individual exposures. But asteroids, because they move, they disappear after you got one picture of them, one exposure. So these colors correspond to the principal colors used to construct color image. So you have red, you have green, you have blue. And so these asteroids, when we combine the image, we can remove them. Our software is smart enough to recognize them and remove the streaks when combining individual images. This is why you did not see them before. But now we will focus on asteroids. It's another 1-minute video. It showcases our unprecedented ability to detect small objects orbiting the sun. You can see motion against the static background of stars and galaxies. And we are only showing asteroids discovered by Rubin, not previously known asteroids. These are all new discoveries that were reported to the Minor Planet Center at Harvard this morning. There are so many of them. Just a few nights of data, just one tiny region on the sky. And now you will see their location in solar system. Let's pause here. So this blue donut, this is simulation of all the asteroids we expect there. And because we only spent few nights to get these data and we looked towards one small region on the sky, all of these new discoveries are found in this one narrow slice of this big donut. In 2 or 3 years, after we start LSST later this year, we will sweep around and discover all of these millions of asteroids. So we had 2,000 in these few nights of data. There are 7 near-Earth objects that have orbits that cross Earth's orbit. None of them is in such position to strike Earth, don't worry. We'll get tens of thousands more near-Earth objects. And we will discover about 5 million new asteroids during the next few years with LSST. This is 5 times more than all the astronomers in the world discovered during last 200 years since the discovery of the first asteroid. So because of this rapid development of technology today, we can outdo all these 2 centuries of effort in just a couple of years. Let us now see another illustration of the ever-changing night sky. We will look at objects that change their brightness. They don't move, but they change the way they look. We will look at stars that are called variable stars because they vary in brightness. They can change brightness on time scales from minutes to years. And by the end of LSST, we'll have data, we will know of about few 100 million variable stars. This is mind-boggling to people who work in this field. LSST will also discover a few million supernovae. Supernovae are exploding, dying stars that are very important for cosmology because it's relatively easy to estimate their distance. We will now take a detailed look at a few variable stars called RR Lyrae. They can become twice as bright in only few minutes, half an hour. That's why we chose them for this presentation. They are in reality about 50 times more luminous than our sun. And they change brightness because the whole star is pulsating like this on time scale of some hours. They are also very useful for studying dark matter in our galaxy because we can get their distances easily too. Here you see this blue star. It's blue because it's hotter than our sun. Our sun would look yellow in this image. And here we are comparing its brightness. Please pause here. So what you can see is color image of that star, average color image, and these 2 observations show its brightness in individual images. And the one in the middle is 30% brighter than the one on your right. It is hard to tell with your eyes, but it is very easily measurable in our high-quality images with our high-quality software that goes through those images. Let's continue. We'll see a few more RLIRE. The next example is even harder to tell with your eyes. It's only 11%. But again, for our powerful, precise software that looks at it, we know it's 11% and not 10 or 12. All these stars are found in our home galaxy, the Milky Way. It's easy to get their distance. To distances much further than we can do today. And so over the next few years, we will map the distribution in the outskirts of our galaxy of both stars and dark matter more precisely than ever before. As you can see, the strength of Rubin and LSST is in huge images, in fast scanning of night sky, in discovery of huge samples of billions of celestial sources, and in studies of those sources with time. How they vary with time. Do they move? Do they change brightness? And that is the real purpose why we built Rubin Observatory. But there is one more thing to tell you today. As we look at the sky, we don't only collect huge samples, we make images of beautiful objects. And so today we want to share with you few beautiful objects, and we chose the Trifid and Lagoon nebulae. These nebulae are giant clouds of gas and dust, and they represent stellar nurseries. They are places in our galaxy where new baby stars are born by those clouds collapsing and becoming hotter and denser until you end up with a protostar, with a young star in the center. So this is the whole image. There are two nebulae. Top right is the Trifid Nebula. This pink nebula in the bottom is called the Lagoon Nebula. Again, this image is very large. It's about as large as the entire Rubin image. And your eyes and our screen are not good enough to display all the detail that we recorded in that region. Again, we will show through video that zooms in around all the vivid detail that is captured in that image. So, ready? Warp 1, engage. Wrong video. How did that happen? Peculiar. All right. We will have to leave that for later. So let me say a few words about what's next for us. That video, by the way, you can see when you follow the link from before, so nothing much is lost. You can enjoy it later. So we've just seen mesmerizing treasure trove of the stuff that LSST will start producing. We are getting to the close of the construction project. We are not done yet. We have some commissioning work to complete, some verification work to complete, but in a few months we expect the project to be completed. We go into operations, and we will start this greatest digital movie of the night sky later this year, and it will go for 10 years. We did not talk today much about science, but I do want to mention over 2,000 LSST scientists who are eagerly awaiting the start of LSST survey. We want to thank them today, thank them for helping us to arrive to this point with their support and expertise. They helped us first build the science case for LSST that led to LSST being ranked #1 in NAS Decadal Survey in 2010, and they also are helping us to build Rubin Observatory. They are organized in 8 topical science collaborations, and they greatly benefit from the supporting nonprofit organization called LSST Discovery Alliance. It's formerly known as LSST Corporation, and that is the organization that started this project. But I also want to emphasize it is not just the scientists who will enjoy LSST data. It is everyone with curious mind interested in what's up there, every child in school we will have tools and materials that our education and public outreach team produced that you can use to be citizen scientists, that you can see in videos in planetaria, that if you're a teacher in high schools, it maps on your science curriculum. All of these will be available from that link QR code in this slide. And so now I will finally finish this brief presentation. The entire Rubin team, and let me add that I was greatly honored by our Rubin team to represent us today. The entire Rubin team hopes that you enjoyed this presentation. Please stay tuned for the exciting discoveries expected from LSST over the next 10 years and beyond. Thank you all here. Thank you all who are watching us over internet. Hundreds of locations in the US and Chile. Thank you and muchas gracias. Thank you to several hundred, close to 300 other locations around the globe. Hvala svima. And thank you for being with us today. And a big thank you to SLAC and Aura, our managing organizations. Heartfelt thank to our funding agencies, NSF and DOE, to our awesome program officers, Dr. Eda Jar, Dr. Kathy Turner, thank you, thank you, thank you. And finally, we are all very grateful to our host today, the US National Academies of Science. Thank you for having us. Greetings to all from the Rubin team. Thank you. This is for the Rubin team. Thank you, Rub. Thank you. We will now continue with our press conference. We will have a panel of Rubin experts that will be answering questions from our media representatives. So I would like our panel to come and join me on the stage, and then we will introduce them once they sit down. Okay, while you are getting on the stage, let's play this beautiful video. We start in the Trifid Nebula. We zoom out. You can see this. Now you can see the background composed of hundreds of thousands of stars. You can see beautiful colors that are due to light from stars bouncing off different types of gas, hydrogen, helium, and oxygen. You can see these dark spots. They are not holes in the sky. They are dark clouds that absorb light between stars behind them and us. They are in the middle. These are not holes in the sky. Here you can see a cluster of baby stars surrounded by this pink emission. These are all new stars that were born in the center. Again, more beautiful dust clouds. There are stars, just as many as outside the clouds, but that cloud blocks the light. And again, such a large image with so much detail, such vivid colors, to produce it in a reasonable amount of time, you really need Rubin Observatory. So if we could go to the last slide. Actually, I think I remember names of all of my colleagues. So let me start with Sandrine Thomas.